All right, welcome back. Today, we are pulling back the curtain on one of the most brilliant, most essential tricks in all of computer science: memory management. It's this silent, invisible magic that lets your computer do what feels like the impossible every single day.
I mean, really think about it. You've got your code editor open, a browser with like 50 tabs hogging resources, maybe a game running in the background, and you're streaming music. You might only have 16 gigs of RAM, but all that software together wants way more. So how on earth does it all work without your machine just crashing and burning? That's the big question we're going to answer today. And hey, for those of you who've been following our operating system series, it's great to have you back. If you're just jumping in, I definitely recommend checking out the full playlist first. Getting a handle on things like processes and scheduling will really make this all click into place.
Okay, so let's get right into it. The absolute core challenge for any modern OS is this: how do you share one finite physical resource, your RAM, among a whole bunch of competing, greedy programs that all want a piece of it, all at the same time? And you got to do it without letting them step on each other's toes. To understand how this works, you first have to get this key idea: the difference between a logical and a physical address. See, when a programmer writes and compiles an application, it's given its own perfect private little universe. Its memory addresses start at 0 and go up in a nice, neat line. That's its logical address space. But in reality, the OS can and will shove that program anywhere it fits in the computer's actual physical RAM. The physical address is where it really lives.
So how do we connect that fantasy world to the real world? Well, every single time your CPU needs to fetch some data, it sends out a logical address. But that request doesn't go straight to your RAM. Nope, it's intercepted by a special piece of hardware, a gatekeeper, called the Memory Management Unit, or MMU. The MMU has one job and one job only: to act as a translator, instantly converting that program's logical address into the correct physical one.
Now, before we landed on the super elegant solution we use today, computer scientists tried a few, let's call them simpler approaches. We're going to take a quick look at these because, honestly, understanding why they failed is crucial to appreciating why our modern systems are so brilliant.
The first ideas were pretty blunt. With fixed partitioning, you just chop up your memory into fixed-size boxes. Simple, right? But what if your program is tiny and the box is huge? Well, you just wasted all that leftover space inside the box. We call that internal fragmentation. So they got a bit smarter with dynamic partitioning, where they create a slot exactly the size of the program. Great, but as programs start and stop, you get all these little unusable slivers of memory left over between the programs, and that's external fragmentation.
And this right here is the villain of our story: fragmentation. It's this awful problem where you might have, say, a whole gigabyte of free RAM in total, but if it's all broken up into thousands of tiny, scattered pieces, you can't load a big new program. It's kind of like having enough Legos to build a castle, but they're all super glued to the floor in different rooms. Useless.
So yeah, a much better way was needed. A way to give every program that clean, simple, continuous memory it wants, while letting the OS deal with the messy, fragmented, physical RAM it actually has. And this leads us to one of the most powerful, most important concepts in all of computing: virtual memory. As the legendary computer scientist Andrew Tannenbaum once paraphrased, programs are just greedy. They will always expand to fill whatever memory you give them. The demand is basically infinite. And it's that constant pressure that forced the invention of a system that could create the illusion of infinite, perfect memory. And that's the key word right there: illusion. That's exactly what virtual memory is. It's not a new kind of hardware, it's a technique. It's a clever, elegant deception, a magic trick run by the operating system and the MMU working together to solve all the problems we just saw. So here's the trick, laid bare. With virtual memory, every single process running on your computer gets to believe it has the entire machine to itself. It sees this huge, perfect, private memory space, all for it. Meanwhile, behind the scenes, the OS is the ultimate puppet master, taking this clean virtual view and secretly mapping it, piece by piece, onto the messy, shared, and fragmented physical RAM.
Okay, so how? How does this amazing mapping actually work? The secret sauce used in basically every modern system is a technique called paging. So let's pull back the curtain and see how the magic actually happens.
First things first, The OS takes the program's big, continuous virtual address space and chops it up into small, fixed-size chunks. A pretty common size is 4 kilobytes. Each one of these little chunks is called a page.
Next, the OS looks at your actual physical RAM and does the exact same thing. It carves the entire stick of RAM into chunks of the very same size. And these physical slots are called page frames. So you've got virtual pages and physical page frames, and they are a perfect one-to-one match in size. Now, to connect these two worlds, the OS needs a map. And for every single program you're running, it keeps a special data structure called a page table. You can just think of it as a translator's dictionary or a GPS. Its whole job is to answer one simple question. Hey, for this virtual page, which physical page frame is it in? Let's walk through it. The CPU says, I need the data at this virtual address. The MMU grabs that address and splits it into two parts. A virtual page number, which is like the chapter of a book, and an offset, which is like the line number on the page. The MMU uses that virtual page number to look up the answer in the page table. The table says, that page is in physical frame number 73. The MMU grabs that number, tacks on the original offset, and boom, it has the exact physical address in RAM. Now this system is already genius. It completely vaporizes the fragmentation problem, because any virtual page can be put into any empty physical frame anywhere. But it also unlocks something even more incredible. What happens when the program asks for a page that isn't even in RAM? The MMU looks in the page table and sees a little flag that basically says, this page isn't here right now. This triggers an event called a page fault. Now, fault sounds like a bad thing, like an error, but it's not. It's a completely normal and planned for event. It's basically a tap on the shoulder for the operating system. The OS then pauses the program, goes and finds the page it needs on your much slower hard drive or SSD, loads it into an empty page frame in RAM, updates the page table map, and then seamlessly tells the program, okay, you can continue now, right where it left off. The program is completely oblivious that anything even happened. And that, right there, is the true magic. This whole system allows us to run dozens of programs at once, each one living in its own protected memory bubble, completely isolated from the others. And maybe most importantly, it lets us run programs that are way bigger than our physical RAM, because the OS only needs to keep the bits we're actively using loaded. This isn't just a feature, it is the absolute bedrock of every modern operating system you use. Of course, this introduces a fascinating new puzzle. If your RAM is completely full and the OS needs to load a new page from the disk, it has to make room. It has to evict a page that's currently in RAM. But which one? How does it choose which page to kick out so that it causes the least amount of disruption? That question. The art and science of page replacement algorithms is a fantastic topic all by itself, and it's exactly where we're going in our next explainer. So if this all made sense and you learned something new, do me a favor and hit that like button, and be sure to follow so you don't miss what's coming next. Thanks for watching.